Okay, so last week we started discussing the resistors, and the last thing we had discussed, if you remember, we were looking at various connections of resistors. We said that if you have a battery, you can connect two resistors in series, which basically means that the same current passes through both of the resistors. And in this case, the equivalent resistance of the system is just the sum. And the current running through the resistor, through the circuit, let's call it I, would be just I times the equivalent resistance. And how we derive this? Well, we basically said that if you consider the potential difference between A and B, since there is a battery connected, that potential difference is A. But at the same time, the same potential difference can be written as the potential difference between A and C, and the potential difference between C and B. And then we said that V, which is defined as I times R equivalent, should be equal to the potential difference across a resistor is just the current times the resistance, I times R1 plus I times R2. So I's cancel, and we just had the total resistance of the system as R1 plus R2. And then we said, okay, we can also connect the resistors in parallel, meaning that different currents are passing through those two resistors. This is one resistor, this is the other resistor. This is R1, this is R2. This is the battery. And then in this case, we said that 1 over the equivalent resistance is given as 1 over R1 plus 1 over R2. And to obtain this result, what we used was, if the total current running through the circuit is I, part of it will go over resistance 1, and part of it will go over resistance 2. And the total current is just the sum. Because if you just consider the current as the motion of charges, when the charges are moving along this wire, when they come here, some of them will go up, some of them will go down. The sum will be conserved. The number doesn't change. And at the same time, we know that the current running through the circuit should be V over the equivalent resistance, whatever it is. Now this time, since the battery is connected across R1 and also across R2, the potential difference across both of the resistors are the same, and the current running through them is just V over R1 plus V over R2. So V's we can just cancel, and we get the expression for the equivalent resistance of resistors connected in parallel. Now, any questions up to here? Now, because from this week, we will be building more and more complicated circuits. So we already know two circuit elements, the capacitors and the resistors. We had discussed pure capacitors. We have also discussed the circuits made up of pure resistors. And now the next question would be, what happens if we combine them? But before going on, let's make this circuit a bit more realistic. You see, here, if you consider that circuit, what we are saying is, across this wire, there is zero resistance. Across the battery, there is no resistance. The only resistance are through these two resistors, which is not the case. At least, the batteries will always have some internal resistances. So when you buy a battery, we will show a realistic battery like this. This is, as a whole, is the battery we have. This represents the internal resistance of the battery. So since there is an internal resistance, the problem is, let's say, you connect this battery to some circuit, some device. So that some current is running through the battery, through the circuit. So this will be our circuit. Now, if you want to measure the voltage provided by the battery itself, what you do is you just take a device that measures the voltage difference and connect it to the ends of the battery. These are the ends of the battery. We cannot just eliminate this one. This is inside the battery. So what we do is we just measure the voltage across these points. Let's say this measures the voltage. This is point A, this is point B. Let's say the V to be the voltage denoted on the battery itself. Let's say it might be 1.5 volts. Now, if you measure the voltage VAB, what will you measure? You see, the battery, this part provides V. But then there is the resistor also. There will be a potential drop across the resistor. What will that potential drop be? It will be just, let's just show it small r minus I times R. This is the voltage that you will measure across the terminals of the battery. You will not measure 1.5 volts, but you will measure something smaller if there is a current running through the battery. So to be more explicit about what we mean when we say that the battery provides 1.5 volts, we define a new concept, so-called EMF. Which is the electromotive force. Just a warning, EMF is not a force. Although its name has this word force, it is not a force. So we will always use the terminology EMF. And for a battery, for example, the EMF of a battery is the potential difference across the terminals when I is equal to 0. So if there is no current running through provided by the battery, if there is no current running through your circuit, then if you connect your potential measuring device to the terminals of your battery, it will show you the EMF. And the number written on the batteries that you buy, 1.5 volts or 1.2 volts or whatever, they are actually the EMF of the battery. So since it's a special kind of voltage, basically it has the same unit. It's measured in volts. Now, this distinction would be important in real life, because in real life, that small r is never 0. Now, let's see what happens if you connect more than one battery to a circuit. Let's suppose you have a couple of batteries, 2 of them. This is R1, this is R2. Let's say this is capital R. Let's also call that capital R. So this has potential V1, this has potential, the EMF V2. then we can ask the question, what will be the current running through my circuit? Well, let's try to simplify the circuit first. So this circuit is, in a sense, equivalent to this circuit. So this is R2, this is R1. What is the equivalent resistance of this resistor? Well, we are just connecting two resistors of the same resistance in parallel, so the total resistance will be just half. 1 over R equivalent would be 1 over R plus 1 over R, 2 over R. So this resistance over here is R over 2. Now, if you consider these resistors, the same current basically runs over all of them, so they are connected in series. So this circuit itself is similar to this one. It's even similar to this one. Here, the potential, the EMF provided will be V1 plus V2. You can just think of it as, just imagine you are carrying a positive charge from this point to all the way to this point. It will gain a potential difference V1 here and another potential difference of V2 over here. So the total potential difference it will see, assuming there is no current running through my system, will be just V1 plus V2. So that's why I can just replace both of those batteries with an equivalent EMF source, let's say, of providing an EMF of V1 plus V2. And the equivalent resistance is just R over 2 plus R1 plus R2. Now I have a very simple circuit with one battery and one resistor. So I can determine the current running through this system. So I, what is I? V1 plus V2 over the total equivalent resistance. This is the current running through all of my system. So this is my I running over here. Now the next question, how much of it goes to the upper resistor, how much of it goes to the lower resistor? This is I1, this is, let's say, this is I2. Well, in this problem, it will be half of it because the resistors are the same. So the current just divides into two. If they were not the same, what you would do is, well, the potential difference across these 2 points, you can go through one resistor. It will be just I1 times R. This should be equal to the potential difference between these 2 points if you go across the other resistor. Because as we had seen before, the potential difference will be independent of which path you choose. I can choose to go like this. The potential difference will be I1 times R. Or I can go like this. The potential difference will be I2 times R. This will work even if the resistors were different. So in this case, I1 and I2, they should be equal. Furthermore, I1 plus I2 should be just the capital I. So I1, which is equal to I2, which should be equal to V1 plus V2, divided by R over 2 plus R1 plus R2, divided by 2. This is the These are the currents running through each one of my batteries, each one of the resistors connected in parallel. Any questions? Well, let's take the same circuit. But this time, let's just reverse one of the batteries. Let's say again, for simplicity, for example, V1 can be 1.5 volts and V2 can be 1.2 volts. This is the typical non-rechargeable AA battery. This is a typical rechargeable AA battery. Well, you can, if you want, you can again think in terms of the analogy with water pipes. You see these wires, the circuit is like our pipes. The batteries, they just provide some inclination in our pipes. They change the height of the different points in our pipes. So a battery with 1.5 volts would be, in this analogy, it will correspond to a pipe like this with a height difference of 1.2 volts. Whereas the other battery, which is 1.5 volts, it will create a height difference which is larger. And this height difference corresponds to 1.5 volts. Now, if you would create such a pipe system, which way the water will flow? Towards the left or towards the right? Right or left? Well, it's higher over here, so the water will basically flow in this sense, pushing the water uphill over here. Well, the same thing will happen over here. We have two batteries. This battery is trying to push a current in the clockwise sense, whereas this one is trying to push a current in the counterclockwise sense. But since this has a larger voltage, at least for these numbers, the current will be running in this sense. So if you imagine the electrons will be running in the opposite sense. Look at this battery. This battery should eject electrons from this terminal, and those electrons should go back and enter from this terminal. That is what this battery would do if it were put alone in this circuit. But in this case, the electrons are pushed in the opposite direction. The electrons are pushed into this terminal, and the electrons are pushed into this terminal, and they are taken away from this terminal. So essentially, you are reversing the battery, and that is basically what is charging this battery in the chargeable batteries. So you just run it in reverse. That is how you charge a battery. Of course, if you want to charge a battery, let's say this is a rechargeable battery, if you want to charge it, you have to push it stronger. It will be trying to push the circuit in this sense. You should use another battery which is trying to push it even more stronger in the opposite sense, so that you will get a you will be able to charge your system. So what will be the current? You see, before this was the current. What will be the current? It's just a minus. You see, V1 plus V2 is kind of the total height difference. In the previous example, both of the pipes were pushing in the same direction, so this wasn't inclined upward, but it was also inclined in the same direction. So the total height difference was just the sum. But now the height difference, this difference, is just the difference. So the magnitude of the current will be given by this number. Now, of course, these are just very simple systems that we looked at. I mean, not all circuits are so simple. I mean, even with these, with the circuit elements we have, we can devise more complicated circuits. Let's assume we have well, here we have two batteries. Each one has their resistances. You can add, maybe they even have some other resistances over here. Here you have another resistor and another one over here, and this point are connected by a third battery. And let me also add another resistor over here, because basically without that resistor, this battery is just short. There is no potential difference between these 2 points without that resistor. Now, we cannot just say that the resistors are simply parallel or the resistors are simply connected in series. Neither we can say that the batteries are connected in series or in parallel. So how do we solve such a circuit? How do we find the currents running through various parts of this circuit? And there what we use is what is called the Kirchhoff's rules. Well, in fact, we had already used the Kirchhoff's rules even when we were discussing the previous simple circuits. You see, what these rules tell us is that at every junction, currents are conserved. Which means that, let's say, if we call this current I, you see here, there is a split. Let's say let's call this I1, this is our I2, this is our I3, I4, I5, etc. So let's just look at over here. At that point, I1 should be equal to I2 plus I3. This is just a charge conservation. Whatever charge enters such a junction, the same charges should leave the same junction. If 5 coulombs enters, 5 coulombs should leave. So this is just charge conservation. And the second rule is also sometimes called the loop rule. in a closed loop, the voltages or voltage changes should add up to 0. But this is also something we had used many times. It basically says that just pick up any point, the potential difference of that point from that point is always 0. But you can start from that point and go around the loop, calculate all the potential changes as you are moving around, and at the end of the day, just reach the same point. There's no potential difference. Just consider, again, just using this analogy with the height and water pipes. Just imagine yourself. What is the change in the height of your position throughout the day? Just 0. You start from your home. You come here to the physics department. On Thursday, you go up. Your height increases, not your height, but the height of your position increases, then you go down. Probably you go to other classes, which might be in the second floor, third floor, you go up and you go down. So your height during the day, your position during the day always changes, but at the end of the day, you go back home. So the height of your eventual position is always 0. The change is 0. Exactly the same thing over here. Let's say, if I choose my point A to be this point, we said that the potential difference between 2 points should always be the same independent of your path. One of the questions in the midterm. So the potential difference of point A from point A should be 0. But I can calculate that potential difference either staying there, or I can just go across this resistor, then across this resistor, across this battery, and it should still add up to be 0. That is the second Kirchhoff's rule. In this example, let's see. Let me give some names to the resistors. This was R1, R2, R3. Let me call this R4. In the above example, well, let's see. What is the potential change as I go from A to this point? This is my resistor R1. There is a current I1 running through my resistor. It's just I1 times R1. That is the potential. The I times the resistance is the potential drop across a resistor, potential change across a resistor. So I times R1. I1 times R1. Well, let's continue with the same circuit. This is the I2 current running from here to here. Well, what is the potential drop from this junction to this junction? 0. Basically, there is no resistance. So let me call this I6. Here we have the current I6. What is the potential change as I go from this point to this point? I6 times R4. I6 is the current running through R4. Now I am continuing my integration to calculate the potential difference. From this point to this point across the battery, what is the potential change? What is the potential drop? It's just V2. Then let's continue. Across this line, what's the potential drop? 0, because there is no resistance. then across from this point to this point, what is the potential drop? V1 or minus V1? Well, you see, we are just summing the potential drops all along. But this battery, this terminal is the positive terminal. This is the higher potential. This is the lower potential. So since I am calculating the potential drops, the potential drop across from this point to this point is minus V2, minus V1. And I'm back to point A. A drop by a negative number is just an increase. That is why we say that as we go from this point to this point, the potential drop created by this battery is minus V1. So you see, in that circuit, we have many unknowns. We don't know this current. This current we don't know. 2, 3, 4, 5, 6 currents. There's a current over there, 7. There's a current over there. We don't know 8 currents. There are 8 unknowns in my problem. So I have to write down 8 equations to determine the 8 unknowns. One of them is this one. You see, in that one, what I did was I started from this point, summed all the potential drops across this loop. Well, I could have done something else. I could have started from point A, went all the way up here, then diagonally, then here. Again, the sum of the potential drops should be 0. Or I could have started from here, went around this loop that you don't see. I could have started from here and went around this loop. Or I could have started here, went around this loop. So all those loops will give you a different equation. Other equations will be just like this. So here, at this point, we know that I1 should be equal to I2 plus I3. That is one simple equation. At this point, I know that I4 should be I5 plus, let's call this I7. So those different equations different loops you can think of, will all give you these 8 equations that you need to determine the 8 currents. Now let's apply these rules to this problem. We already know the solution. So let's try to determine the solution of this problem using Kirchhoff's rules. I don't specify whether V1 or V2, which one is larger or smaller. Let's say I don't know. I have 2 batteries. There is a resistor over here, R1, another resistor here, R2, and these 2 are equal. I labeled this current to be I1, this current to be I2. So basically, I have 3 currents that I want to determine. I don't know capital I don't know I1, I don't know I2. These are the 3 unknowns that I have. Now let's start with the current conservation. Well, current conservation at this junction tells me that the current entering into my system, which is I, should be equal to the sum of the total current leaving that junction. The currents are leaving are I1 and I2. This is my equation 1 for 3 unknowns. I still need 3 more equations, 2 more equations. Now let's go around this loop. Let's start from here. Let me use that loop. And let's go around that loop in this direction, in the direction of the current I. Zero equals, let's start from here. That's my point A. Let's start from here. Now I'm crossing a resistor. What is the potential drop? Well, the current running is I. The resistance is R2, so the potential drop is I times R2. And I know that the current always flows from a high potential to the lower potential, so there's actually a potential drop here. So that's why I don't introduce a minus sign there. Then I continue around my red loop. Well, no resistors over here. So here there is another resistor. What is the potential drop across the resistor? I2 times R. Then I continue along my loop. What is the potential drop as I go from this point to that point? V2 or minus V2? It's just V2 because we are in the positive side, which is at a higher potential, and we go to the negative terminal, which is at the lower potential. So there's a drop of V2. What is the potential drop across this resistor? I times R1. What is the potential drop across this battery, this EMF source? Minus V1, because we are going from the lower potential terminal to the higher potential terminal. So there is a potential, actual potential increase, but a potential increase we can write as a negative potential drop. So this is my second equation. Now let's write the third equation. For the third equation, let's go around this loop. In this direction. Let's start from this point B. The potential drop should sum up to be 0. Well, what is the potential drop as I cross this battery? It's carrying a current I1. I1 times R. Well, I'm going along the blue loop, so there is no resistance. Now there is a resistor, which creates a potential difference. What is the potential drop as I go from this point to this point? It's definitely I2 times R. But you see, the current is running in this direction. So this is a higher potential point than this one. So here, as I go from this point to this point, there is an actual potential increase, not a decrease. But an increase, again, we just write as a negative decrease. And this is my third equation. Well, you can ask, what if I chose a different loop? Well, let's choose a different loop. Let me choose such a loop now. I start from this point A. I follow the red loop until the junction, but I don't go down, I go up. And then close the loop. Doesn't it give me a fourth equation? Well, let's write that fourth equation. Again, let's start from A. What is the potential drop across the resistor R2? R2 times I. This is the potential drop across the resistor R2. Then we are back here. We are crossing this resistor, capital R. What is the drop? The current is I1, the resistance is R. I continue along my loop. What is the potential drop as I cross this resistor over here? Plus V2. Now I cross this resistor over here of resistance R1. What is the potential drop? The current is I, the resistance is R1. Now I am crossing this second battery. What is the potential drop? Minus V1. But you see, this fourth equation is nothing but the second equation plus the third equation. If I just sum these two equations, here I have I2 times R. Here I have minus I2 times R. They just cancel. And instead of I2 times R, I end up having I1 times R. But that is nothing but this equation. This term is this one. Instead of I2 times R, I have I1 times R. But when I sum these two, these cancel and this one remains. And then I have V2, I times R1, and minus V1. This is just 2 plus 3. So essentially, you can imagine even more complicated loops. You can just imagine going one way, going twice around the loop, or going once in one direction and then coming back again. But all the equations that you will obtain will eventually be reduced to these three equations. So let's solve them. Let's see, they actually give us our previous results. You see, this third equation is trivial to solve. This already tells me that I1 should be equal to I2. And combined with the first equation, if you combine with the first equation with this one, it just tells us that I1 is equal to I2, which should be equal to capital I over 2. Now let's just substitute it into this equation. Let me take this one. This is the equation we didn't use yet. Let's express everything in terms of capital I. So capital I times R2. Well, I2 is capital I over 2 times R plus V2 plus capital I times R1 minus V1. Should be 0. I times R2 plus capital R capital R over 2 plus R1 should be equal to V1 minus V2. And I should be equal to V1 minus V2 divided by R1 plus R2 plus capital R over 2. And this is indeed the result that we had obtained before. For the simple circuit, we don't really need to use the Kirchhoff's rules, but Kirchhoff's rules basically works for all kinds of circuits that you can imagine. And another thing that you should pay attention to, you see here, I didn't specify whether V1 or V2 was larger than or smaller, or large or small. It might be that V1 will be 1.5 volts, but V2 might be 1.2 volts. This solution will still hold. Or it might also be that V1 is actually 1.2 volts, whereas V2 is 1.5 volts. In that case, the current will turn out to be negative. But the negative current basically would mean that this I is not running in this direction, but it's just running in the opposite direction. So before using the Kirchhoff's rules, I don't even need to know the directions of the currents. I just assume some direction. Once I use the Kirchhoff's rules, I write down the equations that determine my currents. And once I determine the currents, it might turn out that the currents will be negative. If the currents are negative, that would only tell me that my initial guess in the direction of the current was wrong. So I should just change the direction of the current. The current is actually running in the opposite direction. That's the only thing that the negative current would tell me. Any questions? Yes, there is a question. We will use it. On Thursday, we will start the circuits with capacitors. So see you on Thursday.